Hello, everyone. What I want to do is continue on from last time. So remember, basically, before what we had was if Sn was the partial Fourier coefficient, Fourier sum, f hat n e 2 pi I n u t rather. These were the Fourier coefficients. Then we have this nice formula 0 to 1 sine 2n plus 1 u over sine pi u f of t minus u du. And this was called the Dirichlet kernel. And because if you integrate this, because this, remember, is really n equals minus n e to the 2 pi I n u. So trivially, you integrate this from 0 to 1, you're just going to get 1. Everything vanishes. Each term integrates to 0 except the n equals 0 term. So remember what that means. That means we have this very convenient, basically f of t is going to be 0 to 1 times this Dirichlet kernel. Because you're literally just taking f of t times integral of 1. And the conclusion is that this here is equal to absolute value of 0 to 1 sine 2n plus 1 iu over sine iu f of t minus u minus f of t, excuse me, du. And to be clear here, f, remember we said is an L1. Basically L1, that's one periodic functions. So remember what this is, f defined on all of the real line, where well, at the very least f measurable, so I can integrate it. One periodic, and it's integrable on 0 to 1, or really any interval of length 1. And yeah, you can put any interval of length 1 here, and you'll get the same class of functions. Yeah. So yeah, you can replace this here. A1 plus A. And here, this integral literally is this, we proved that for A1 plus A, absolute value of f. And I should say, of course, you can do all this analysis for, in general, 2L periodic functions that are integrable over any interval of length 2L. The formula gets, the conclusion here and everything gets modified a little bit, but not much. I've showed you before how to go from one periodic functions, a general 2L periodic functions. If you want to do that, by all means do that. But maybe at the end I'll show you. I'll just write down the general formula actually. Might as well. Real quick. So if f, let's say, is an L1 0 to 2L, so in particular, let's say f is 2L periodic measurable. The integral from 0 to 2L of absolute value modulus f is finite. Yeah, so this is going to be S and F, capital N. A bit of a more of a pain to write, but that's fine. To L, sine 2n plus 1 over 2L pi u over, see if I could squeeze this in, pi u over 2L. Otherwise, it's the same f of t minus u minus f of t du. Okay, so I mentioned the proof strategy to show that this is going to go to zero, then goes to infinity. And remember that was, let's take this thing here, call it g t of u, and we want to show that basically that this is L1, more or less show that this is L1, and we need conditions on F to show that this is an L1. Then the Riemann-Lebesgue lemma will give us that Sn f of t minus f of t goes to zero as n goes to infinity. And to be clear, this is for a fixed t. So it's a local, it's going to, well, we'll see what we need to do that. And it's very hard to prove uniform convergence through this formula. Typically, if you want to prove uniform convergence, you use the Weierstrass M-test or that Dirichlet summation theorem that we had before that was proved using summation by parts. Yeah, those are typically used to prove uniform convergence. This is typically how you prove we have convergence to the function we want to begin with, to the function whose Fourier series we're taking. Okay, so yeah, remember, and I stated a little differently, that I'm going to state it here differently than I stated last time. So remember what the Riemann-Lebesgue lemma is. And if you happen to be watching this on YouTube and you're not taking my course now, forget about what I just said a second ago. So Riemann-Lebesgue lemma in general is the following. F is an L1. Let's do G. Plus or minus infinity. And it's sines and cosines, but for us, we'll just write it down using sine. Sine, let's say lambda u. This equals 0. I think it's useful not to prove it, but to explain why the Riemann-Lebesgue lemma is true. And I'll have for homework, you guys basically expand this outline. So it's two steps. One, if, let's say, g is a constant times a characteristic function, then this is absolutely trivial. That as lambda goes to 0, we get 0 because this is A to B, pull out the C, sine lambda u. And that's going to be minus c over lambda, just calc 1 cosine b lambda minus cosine a lambda. This goes to 0. Okay. And yeah, so what is going on here? So let's say we do something like sine 100x. Okay, so you can barely see this. Let me zoom in then like a bit. So yeah, you could see clearly that over a fixed interval a to b, I can make this 1,000. I can make this anything really, really large. And you're going to get a lot of oscillation within that fixed interval. In particular, you're going to have a lot of the graph is positive and negative. You're going to have a lot of positive and negative area canceling out over the integral from any fixed interval a to b. So that's exactly what calculus tells you is happening. Um, yeah, and that's reflected by let's go back. That's reflected in getting this lambda from the integration. This lambda comes from, or intuitively, this lambda comes from the fact that this has over a to b a lot of positive and negative area canceling out. You have a lot of oscillation going on. And cancellation is going to be a theme of this course and in general Fourier analysis. So, step two is well, basically functions of the form linear combinations of functions of step one from step one are dense in L2. So right. Okay. Yeah, so that's the basic outline. Linear combinations of step functions, or rather linear combinations of a constant times characteristic function of an interval, they are dense in L1, and for such functions, it's sorry, for such functions, it's basically trivial. So um okay, so let me state the following theorem called Dini's theorem from late 1800s. So Dini's theorem is as follows. Get it? Right. So actually, you can state Dini's theorem in this setting, and it doesn't change one bit. So I'll even do that. I'll prove it just for L equals 1/2. L, a one periodic function. So if we have a 2L periodic function, that's L1. And if there exists delta bigger than 0, where the following is true. So it's like an integrable differentiability condition, sort of. It's hard to motivate it, I suppose. Typically, delta is very small. So if this is true, and it's a bit stringent, as we'll see in a minute. Not always, but So we have the SNF converges to F, right? At T. Okay, so as before, for convenience, we're going to assume L is 1/2. Okay. And also what I'm going to do is instead of integrating from 0 to 1, it's going to be more convenient to integrate from -1/2 to 1/2. So yeah, it's going to be -1/2 to 1/2 sine 2n plus 1 pi u over sine pi u f of t minus u f t dt. Okay, so what I'm going to do, just as I mentioned, the strategy is to basically prove that this is L1. All right. And yeah, so it might actually, instead of literally proving that this is L1, it might be a little easier to just basically break the integral up into two pieces. Okay. And basically show each one goes to 0 as n goes to infinity. It's basically the same thing. It's just a little bit cleaner, I suppose. So in other words, what this is, it's going to be less than or equal to the following integral. So we're going to go -1/2 to minus delta, delta to 1/2, GTU sine 2n plus 1 pi u. And then minus delta to delta, assuming delta is less than 1/2. I'll call this A and B. All right, so before I before I do anything, we need two facts about sine. First is that as long as u is between minus pi over 3 and pi over 3, and I'll quickly prove this. So this is less than or equal to absolute value of sine u is less than or equal to, this is always true, sine u absolute value is less than or equal to absolute value of u. But in particular, what's important is this part right here, actually. Yeah, so we actually don't even need this part. Okay, so why is this true? Well, very trivially, as long as u is not 0. So if u is 0, they're both 0, so that's basically trivial. So just use mean value theorem. Obviously, sine u is 0, sine 0 is 0. Right. So this is going to be equal to cosine star 4u star between 0 and u. So in particular, right, so in particular, because u is between minus pi over 3 and pi over 3, right, we have u stars also between minus pi over 3 and pi over 3. So this here is actually going to be between 1/2 and 1. So in particular, yeah, so in particular, it's going to be bigger or equal to 1/2. Because cosine, uh, yeah, cosine between minus pi over 3 and pi over 3 is between 1/2 and 1. So yeah, multiply both sides. So this is bigger or equal to 1/2. So we're done. Okay, so 2 is that if u is between minus 1/2 delta, delta and 1/2, sine pi u is bigger or equal to sine pi delta. And this is pretty trivial just from the graph of sine. One, it's even bigger. Don't want to dwell on this too much. Okay, so let's graph y is sine pi u. So the max is, of course, at 1/2 minus 1/2. All right. So normally, so let's plop in minus delta here and delta here. So normally it's going to go like this. And then it's going to go up like that. Okay, I don't think it's going to let me. No, of course it won't. Why would it do that? Guess I can make it white. Yeah, okay, but we're between, so we're omitting delta to delta basically. So let me make this white. So yeah, we're omitting all this here. So you can kind of see trivially work. Yeah, it's annoying. There we go. Okay. Right, so you can see just trivially graphically that yeah, if we omit minus pi to pi, then at the least that absolute value sine pi del u is going to be is sine pi delta. Okay, so that basically proves that. All right, so now yeah, we're actually almost done, really. Okay, so for A, we are going to use this fact here. So remember, this is what GT of u is. So GT of u. So let me do this. Sorry. 1/2 minus delta. Delta and half. Okay. So this is going to be equal to f of t minus u minus f of t over sine pi u times this characteristic function. I think at this point, just the writing is probably the most annoying part of this proof. I mean, really, the proof is pretty trivial now. So we know this is big or equal to sine pi delta. So the whole thing is going to be less than or equal to 1 over sine pi delta. That could be small, but it's not 0 in the bottom. And let's just stick a characteristic function. We don't really care. Minus 1/2 to 1/2 gets the job done. And just smash an absolute value. And this is trivially an L1 of R because this is just an interval of length 1. And this is f of t, so it's just a constant. You can certainly integrate a constant over something of length 1. And f is assumed to be L1 of minus 1/2 to 1/2. Same thing, 0 to 1, because f is 1 periodic. So just easy substitution. This will be an L1. So, all right. So, yeah. So the point is for A, it's not clear. You can basically write this as integration over the real line times this characteristic function, gt of u. That is going to be an L1. So Ramon Lebesgue immediately says that A goes to 0 as n goes to infinity. And B is very similar. Right, so I'll try to do this nice and quick. Okay, so this equals characteristic function minus delta delta. Assume delta, as before, is less than pi over 3. Well, it's certainly less than that if it's less than 1/2. So it's terrible. But we're basically doing the same thing, but using the other fact. So this is going to be so I definitely do not want to just smash in absolute values here. Okay, so this is less than or equal to minus delta of u. So remember, sine pi u is going to be bigger or equal to 1/2 absolute value of u. So this is going to be yeah, so this is going to be less than or equal to 1 over, or sorry, 2 for delta small enough. Pi, right, 2 over pi, absolute value of basically the integrand from that Dini condition. And sorry, that should be f of t here. Sorry about that. This is an L1 of R. That's literally the Dini condition. The Dini condition tells me that this is finite. Okay. So again, we can think of B as integration over the real line of this characteristic function from minus delta to delta times GTU. That is a L1 function on the real line. So Ramon Lebesgue, again, I guess I forgot the du here, but whatever. So Ramon Lebesgue, again, gives me that B goes to 0 as n goes to infinity. Now, one thing I want to make clear is that Ramon Lebesgue doesn't give us any uniform convergence whatsoever. It's just that for each t, this function GTU is an L1 in both of these cases, and therefore, as n goes to infinity, the integral goes to infinity. So to get uniform convergence, you typically have those two tools, either Weierstrass M-test or that Dirichlet summation condition that we talked about and did a lot of examples with. A thing we used summation by parts to prove. But so kind of combining the two together, the point is this gives us a condition where the Fourier series of f converges to f. And typically, if you want them to get uniform convergence, use a Weierstrass M-test or the Dirichlet summation theorem. All right. Okay, so some easy examples. So first of all, a very easy kind of example of these kind of functions that satisfy this Dini condition would simply be functions that have both a left and a right derivative. So sorry, just looking for Okay, so now let's suppose f is continuous at t. It's also L1 periodic. But let's assume it's continuous at t. Okay. Let's define f prime of t plus to be the right derivative and define this to be the left derivative. If we're assuming they exist, they might not be equal. Let's assume they exist. So let's say this is u goes to 0, and we'll extend this definition. It's a very basically this definition assumes continuity. Otherwise, you have to modify it a little bit. It's the same thing, except u goes to 0 from the left. So let's do t plus u. So actually, what you could do then, if you think about it, we can make it a minus, but then make this a minus. Then we can make that a minus. So this is going to make, so here the point is minus u is going to be positive. So it's t plus something positive as that something positive goes to 0. Right. And here we can do the same thing. It looks a little funky, but matches the Dini condition basically. Again, the idea here is minus u is negative. So it's t plus something negative going to 0. Okay. So pretty trivially, if both exist, then this quantity here is bounded. on some very small interval minus delta to delta. Um, just basic properties of limits. So, well, you're just integrating a bounded function from minus delta to delta. So this pretty trivially, and I did that again, it's f of t here, not f of u. Sorry. Yeah, so that's pretty trivial. So yeah, for example, uh, let's just go back to that kind of function when we did in class. If you are in my class and you're watching this, the example we looked at for solving the wave equation. Okay, so remember, um, f of x equals x, 1 minus x. So here L is, instead of 1/2, L is going to be 1. So we're looking at a 2 periodic function. Next, then oddly, 2 minus 1, 0. So we drew this before, but I'll draw it again. So we got 1, 2, minus 1, minus 2. I'll go to minus 3. Good measure. So it was basically like this, and then like this. Yeah, really annoying. It does that. Yeah, so it's basically like that. Something like that. Okay, so yeah, certainly this is differentiable. Okay. So that proves that particularly for anything between -1 and 1, and by periodicity, any real number, we have convergence of Fourier series by Dini's theorem. Any t and r, f of t, we computed the Fourier series, and if you're not in my class and you're looking at this, well, yeah, it's an easy exercise to compute the Fourier series here. So it's 4 over n cubed, I cubed, sine n pi t. Yeah, again, like the derivatives exist everywhere here, so Dini condition is trivially true. Okay, so yeah, remember what the derivative looks like. And still the Dini condition is going to be fine. It's when I take two derivatives that we need something a little more powerful, or not more powerful, but a little different than the Dini condition. All right. So yeah, remember this is the derivative is 1 minus 2x. So it's going to be 1 minus 2t. Guess I went from x to t, but that's fine. So it's going to be from 0 to 1. And you can check that's going to be extended evenly to -1, 0, like we did before. I think I left that for you to check. So t equals 0. It's going to be 1, -1. We got 1/2, 1, 3/2, 2. Just go like this. This is 1/2, 1, 3/2, 2. Same thing here. Like this. Okay, so yeah, we proved, sorry, it's gonna go down. Right. Okay, so yeah, Dini's condition, you can actually, I mean, we proved that the derivative is going to be the termwise differentiated Fourier series. So you just termwise differentiate what you have here. But even if you didn't know that, you can just literally compute the Fourier series for this function, and you will see you're going to get an odd, basically what you would expect it to be, 4 over n squared pi squared. Again, this is by periodicity. It's true for everything between -1 and 1, and so by periodicity, it's true for anything in a real line. Because at every point, this function has a left and right derivative. So Dini's theorem, that condition is true. Okay, so clearly now there's going to be a problem with trying to apply Dini's theorem to like a second derivative here, because it's not clear at all what to do. How do you define kind of the second derivative here at these problematic integer points? And so remember, basically the second derivative function is going to look like this, and it's pretty typical. This is fairly typical of this is something we do want as a Fourier series, and we do want if we termwise differentiate, well, we actually so actually let's ignore that. It's kind of hard to even, you can't really ask the question, does Dini's condition hold true? Because it's, what do you even define the second derivative to be at yeah, at that point? So what we proved, actually, remember that this is going to be termwise differentiate one more, and odd 4 over pi n sine pi n t. T not an integer. And so what we'll actually prove is that the Fourier series, whenever you have jumps like this, and we'll prove that in a minute, whenever you have jumps like this, the Fourier series is going to converge to the average of the jumps which is exactly is what happens. In this case, the average of the jumps here is just 0. And this makes sense. You plug in an integer, pi n times an integer is just 0. So, yeah. So we're going to prove that in the next video.